Alright, this is chapter 11, which is the first chapter of Unit 3. So, overall, this unit kind of focuses on intermolecular forces and some reaction phases and stuff like that. There's a lot of math, there's a lot of concepts. It kind of brings everything together. So, chapter 11 starts off pretty simple. It literally defines what a gas, liquid, and solid are. Um, but I think most of you know what the differences are, but I will quickly define them. A gas have very far apart particles. They possess complete freedom of motion. Liquids, they're closely packed, at least in comparison to a gas, but they retain freedom of motion and they change rapidly and they are amorphous. As you can see here, there's no real rhyme or reason, there's no shape, there's no pattern, they're just kind of random. Same with gas. Solids are closely packed in an ordered array, like an order, like a specific pattern, and their positions are fixed most of the time. They do not change unless there's energy put into them. In general, the state of a substance depends on the balance between kinetic energy and the intermolecular forces. So a solid has a high amount of intermolecular forces keeping them together, and a low amount of, well, a relatively low amount of kinetic energy is keeping them together. Keeping them apart, sorry. Then a liquid, kind of a middle ground, and a gas has a high amount of kinetic energy in the particles and a low amount of intermolecular forces keeping them together, relatively. So, let's define what intermolecular forces are, because I might have just said something you did not understand. So intermolecular force refers to the forces that keep things together, keep liquids together, keep solids together. So if we look right here at this pretty crudely drawn diagram, the H2O molecules are kind of almost bonded together, not really, but they are kind of drawing near each other where the negative oxygen, draws in the positive hydrogen so that they're kind of connected but not really bonded together. So they're closer and they're more or less, I guess, following each other or connected. And a chemical bond refers to just like the actual bond, like the bond between a hydrogen and oxygen. An intermolecular force is not that strong, it's just the force kind of loosely connecting them together. Well, now you might be thinking, what do IMF forces determine? What do they do? Well, intermolecular forces in general, they just refer to the forces between molecules. So they would kind of come into play with boiling point, freezing point, um, all the phase changes, because if something has a high amount of intermolecular forces, they will need more energy to go through these phase changes because they're very strictly connected together. So for example, a liquid with high intermolecular forces will take more energy to boil because there's more intermolecular force keeping them together. This is not the same thing as, again, it's not the same thing as an actual bond. It's more like a friendship almost, I guess. I don't know. It's like a loose connection. So there are three types of IMF forces. There are London dispersion forces, there are dipole-dipole forces, and there are hydrogen bonding. And that's an order of strength. So dispersion forces refer to, and I'll draw a little thing. Pretend this is an atom. Atom A, sure. So atom A has some electrons. Let's say it has 4 electrons just sitting around. So these 4 electrons can move around randomly outside of their little sphere and go out here and create a positive charge, where the positive charge is over here and the negative charge is over here. This creates a temporary charge or temporary polarization that causes a temporary or weaker intermolecular force. And this scales with the size of a molecule. So let's say we have a larger molecule, or atom, sorry, a larger atom. And this also works with molecules, but we'll start with atoms. Let's say B. B has 16 electrons. Let's pretend that's 8, and then there's 8 out here as well. 1, 2, 3, 4, 5, 6, 7, 8. So since there are more electrons out here, that means that there's a higher chance, and there's less interference from the atomic nucleus because they're farther away, where there is a higher chance that these electrons are temporarily leaving the cloud and polarizing temporarily, maybe creating a negative charge here and a positive charge here, creating these temporary intermolecular forces. Thus, although they are on the weaker side, they still matter. And we call those dispersion forces. And again, they scale with the size of the atom or the molecule. So a larger molecule will have greater dispersion forces. Now let's look at dipole forces. Dipole forces refer to the permanent charge that a molecule may have, like H2O, which has a permanent negative charge here and a permanent positive charge here. This is a much stronger intermolecular force where the hydrogen will always have a positive charge and the oxygen will always have a negative charge. Therefore, they have a more prevalent IMF, more prevalent boiling point. Like, they are more important. But let's not underestimate dispersion forces. And then finally, we have hydrogen bonding. Hydrogen bonding also is in H2O, but it is also in HF and like HN, H3N. I don't know if that's real, but like something like that. Where hydrogen bonding refers to the bonding between hydrogen and one of 3 elements, and these are the most electronegative elements: fluorine, nitrogen, and oxygen, otherwise known as NOF or NOF. So since these uh, atoms are so electronegative, if hydrogen bonds with any one of these 3, it creates a very polar bond, which creates a much stronger IMF force. So, for example, a H2O, which has this very polar OH bond right here, or OH bond right here, it is so much more polar than a, a different type of molecule that it is a much stronger intermolecular force because of how polar the bond is between a hydrogen and oxygen. Same with HF. Fluorine, as you may know, is the most electronegative atom. So the polarity between hydrogen and fluorine, that bond is so great that it creates these very permanent and like strong charges where hydrogen is positive and fluorine is negative, creating those IMF forces. So yeah, that is that on IMF like classifications. And then we have 2 kind of applications of IMF forces: viscosity and surface tension. Viscosity kind of refers to the thickness of a liquid, like how motor oil or maple syrup has a very strong viscosity or very high viscosity. It's very thick, while water and I guess like I don't know, water is not very viscous, so it has a low viscosity and it kind of flows easily. It's very thin. So viscosity is related to IMF forces because it relates to the length or the size of a molecule. So let's say you have a very long molecule like butane, or I mean not butane, like decane, which is like 10 carbons. I think that's 10. Where it's a very large molecule, therefore it takes more energy for it to move, so it's slower. Well, we have like H2O, which is really small compared to decane, so it moves a little faster. Therefore, the larger the molecule in general, the larger the molecule, the more viscous it is, and the smaller the molecule, the thinner it is, or the less viscous it is. And then with surface tension just refers to the strength of the intermolecular forces. So a molecule with very high surface tension is going to have very high IMF forces. So H2O has very high surface tension. If something were like if a very small insect were to walk on water, it could because of how pretend this is like a water walker. I don't know. I don't know what they look like. They can walk on the water because they're first of all they're light enough and the water is charged enough that it can hold up the insect because of the little charge intermolecular forces. Now, a molecule like methane, which is not charged at all, has no intermolecular forces, CH4, pretend it's a liquid, it's a gas, but pretend it's a liquid. The little thing would sink. Oh no. Because it has no or very little IMF forces, all it has are those London dispersion forces, which is not enough. So surface tension, again, it refers to the IMF forces. And again, viscosity refers to the relative size of the molecule. And I think that's all. Yeah, that's all for 11.1 to 11.3. Next video, I will be going over 11.4 to I guess like 11.5 or 6. This is kind of the more mathy part, the phase changes, and things kind of start to get real. But yeah.